Hello, everyone. Thank you for joining us today. We have an interesting guest, Alix, because he's presenting his work about predicting and understanding human choices using PMCNet with an application to airline itineraries. My name is Jiri, and I'm a stream owner of machine learning in economics with ACE, and I specialize in AI solutions capturing human behavior through cognitive sciences and machine learning. And I'm honored to have Alix, Lheritier, and Omar Nada joining the session today. Alix is a machine learning researcher at Amadeus IT Group, and he's the presenting speaker today. Last but not least, Omar is joining us as well, and he's also a stream owner of Recommender Systems, active researcher with ACE, and last but not least, he's a senior data scientist at Royal Bank of Canada. Also, let me introduce ACE briefly. Aggregate Intellect Socratic Circles is a community of machine learning practitioners and researchers who have gathered around three topics in AI, that is research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject of areas. To see more, visit ai.science and log in to access slides from this and other sessions and many more. Please make sure you also subscribe to our YouTube channel ML Papers Explained to get notified about all the live sessions and other free content we publish. We currently have 15 different streams that are focused on various machine learning topics, and this session is in machine learning in economic streams. And I hope you will enjoy it and come back. So now I would like to emphasize the motivation of this work because I maintain that the choice modeling is an evergreen topic in behavior economics that has been modeled and explained through cognitive sciences, but recently more advanced and accurate machine learning approaches has been proposed. And Alix works elaborates on the two approaches here. And there are several classes of machine learning models, for example, multinomial logit or random utility models that aim to find statistical models capturing the human behavior. Moreover, the inference through machine learning models suffers when examples of each alternative are scarce, and the inference is inappropriate when new alternatives are present in the test time. However, Alix shows that traditional choice model classes and axioms are unable to express empirical observations from modern behavioral economics like context effects. He will tell you more about. And there has been also previous attempts to solve the issue through pairwise choice Markov chains. This case is often observable in real business related data sets, right, like airline booking itinerary. However, pairwise choice Markov chains are free of several axioms. And even though PCM models seems appealing, it's based on maximizing the log likelihood of the rate matrix for the observed choices, and it tends to overfit. I see the main contribution of Alix's work as a design of a generic neural network with injection of the knowledge from behavior economics, and the fact that from each set of alternative, only one is chosen. Last but not least, Alix's approach utilizes a good theoretical knowledge of probability choice Markov chains and non-parametric methods to make an amortized inference that can handle even infinite size universes. And now I will pass my word to Alix.
Thank you, Jiri, for the introduction and for inviting me. Thank you, Omar, also for co-hosting this session. So, so I'm going to present my work on predicting and understanding human choices using an architecture, neural network architecture called PCMC-Net. So I am from Amadeus, and so I will show you my work and also some work that I did with some colleagues. So let's start with the discrete choice modeling. So the basics. So the idea is to have to model statistically the human behavior when people have to choose among a set of discrete alternatives. So these typical examples of applications are consumer purchasing decisions, choices of schooling or employment, commuter choices for modes of transportation. And let's consider some particular example. Here we have a universe of 4 alternatives: car, bus, train, and airplane. So we might be faced with a subset S containing car and bus only. So discrete choice model is a probability distribution over these alternatives. For example, here you can assign 1/2 to each alternative. So these models can also be conditioned on characteristics of the individual making the choice. Like here, for example, we have the conditional distribution given that this individual is violet, let's say. Okay, so this sets up a little bit the notation and the problem. So what are the limitations of traditional choice models? Let's first consider the multinomial logit model. This is the classical model. This is based on the following assumption, that the probability, the ratio of the choice probability of 2 items is independent of the set in which they are contained. So it's independent of the other alternatives contained in the set. So this is called also independence of irrelevant alternatives. Okay. So there is another very important class of models called the random utility models. It's a larger class that contains the MNL model. And I am not going into the details of how it is defined, but the important thing here is that they exhibit the following property that is called regularity. It means that if we consider some alternative A in some set S, and then we consider a larger set S prime, the probability of choosing A can't be larger in this larger set. So the problem with this, at first it might seem reasonable to have such a property, but in fact it prevents these models to represent some context effects like the attraction effect that I'm going to explain with an example. So first consider these 2 choices of popcorn. We have the small bucket and the large one costing $3 and the other one $7. And for example, most of the people tend to prefer the smallest one because they don't want to spend too much in popcorn. And what happens when we add a third option in this set? We have the new set S prime, and this new option is a medium bucket, but that has a price close to the large one. And now people will tend to see the largest bucket as a bargain because for only 50 cents more, they get a lot more popcorn. And now people tend to prefer the largest ones. This was observed in some experiments. It's a classical example of attraction effect. It has other names like asymmetric dominance and others. Okay. In order to overcome this kind of limitations, to be able to represent these effects and others, recently Regain and Ugander have introduced a new class of models called Pairwise Choice Markov Chains models. It was presented in New Reefs 2016. So they allow to escape the independence of irrelevant alternatives and regularity. And they are defined as follows. They are based on a continuous time Markov chain. Here, the Markov chain is defined with a transition rate matrix. In essence, I mean, we can interpret the transitions between the states. The states represent each of the alternatives. So we have transitions from each of the state to each other. And this can be interpreted as preferences between the pairs of alternatives of the universe. So the choice distribution is defined as the stationary distribution of the Markov chain when restricted to the particular set under consideration S. The existence and the unicity of this distribution is guaranteed by the constraint, the following constraint, that the transition rate between the alternative A and J and the opposite from J to I, the sum must be positive. Okay. So this is the definition of the model. So let's see how it accommodates the previous example. If it's able to represent the previous situation. Again, consider the small and the large buckets. We have transition rate 1 from small to large and 2 from large to small. And here we observe the stationary distribution of 2/3 of people preferring the small one. When we add the medium one, keeping the same transition rates between small and large, now we add a medium one with the following transition rates, 3 and 20. And now we see that the new choice distribution is putting more mass on the large bucket, as we observe in real life experiments. And okay, so some properties of this class of models. First, it contains the MNL class, so this is good because in many cases they are allowed to they are good to represent the observations. But they also exhibit this interesting property that is called contractibility that I'm going to explain through an example. Consider a choice between, it's a classical example from the choice theory literature. Consider a choice between 3 musical recordings. Okay, we have one of the Beethoven 8th symphony conducted by some conductor X, the choice B2, that is the same symphony conducted by another conductor Y, and the third one, a Debussy quartet conducted by Z. So when compared to D, B1 and B2 are indistinguishable in the sense that, okay, we have the same preference over D, okay, with respect to B1 or to B2. But someone may have some preference between the conductors X and Y. Okay, so when we have these kind of situations, we can define a contractible partition that groups the similar alternatives. That is the B1 and B2 into a set. Okay, so when a PCMC model contains such a partition, the relative probabilities of selecting from one of these sets is independent from the preferences between alternatives in the same set. So this is a nice property that is satisfied by these models, and that also implies the following one, which is called uniform expansion. That is, if we add the k copies of each element of a set S, the probability of choosing any element of a set of copies is invariant to k. So this is something reasonable and not too limiting for the representation power of these models. So previous approaches for inferring the parameters of these problems, of these models, is these are the ones presented in the original paper from Bragain and Ugander. So the direct approach requires to estimate a quadratic number of parameters. I mean, it's quadratic in the size of the universe, because for each possible pair of alternatives in the universe, we need a transition rate to estimate. So the problem is the following, and it corresponds to our application. When we have alternatives that are identified by their features, that is, for example, when we are looking for flights, we can have some specific flight from some origin to some destination, but the problem is that the price may vary over time. One day is one price, and the next vary with time, let's say. So the problem is here that we have a potentially very large and even infinite universe. So we need something else to estimate these parameters, a different approach. So another approach the same author proposed is a linear parameterization, but still it requires fitting a number of parameters that is linear in the size of the universe, which scales poorly too. So this is where we introduce I introduce my approach, which is called PCMC-Net. So it's a feature-based PCMC. So it's a neural network architecture. I presented this work in iClear this year. And okay, so I'm going to describe this architecture. So it has first an input layer that takes as input the features of the alternatives, and also it allows for individual conditioning. So it also takes as input the features of the individual. Okay, then it has a representation layer that allows to transform to get useful features from the raw features that can be anything like images, text, and so on. So it's depending on what you get as input, you should put the good components for to learn useful features like convolutional networks and so on. And so then we have a Cartesian product layer that will combine all the alternatives by producing all the possible pairs. And for each pair, it will go through a transition rate layer that is a feed-forward neural network that will compute the corresponding transition rate. So here's what we call amortized inference. That is that we are using these parameters, the parameters of this layer. These are reused for all the pairs of alternatives. Instead of having one parameter for each possible pair, we have a set of parameters, WQ, that is reused for all the pairs of alternatives. So here we allow to decouple the size of the universe with the size of the parameters. Then finally, we have the stationary distribution layer that simply solves the equation, the linear equation that that allows to find the stationary distribution, so the choice probability. So this whole network can be trained with stochastic gradient descent with backpropagation. And I also show in this paper that if the network is given enough capacity, this PCMC-Net can approximate any PCMC model arbitrarily well. So we are not losing anything. So then it's easy to show that contractibility and uniform expansion are maintained. And so now let's consider an experiment on synthetic data with context effects. So this comes from this paper of True Blood and others from 2014. The idea here is to consider two alternatives, A and B, with two features, two attributes, and then we are looking at the preference for A over B and how it is affected when we add a third alternative, C. Okay, so the square is all the possible positions for the alternative C, and the shade of gray indicates the preference for A. So a lighter gray will indicate a higher preference for A. So let's consider three cases. First one, okay, we are going from the set AB to a larger set S prime. So if we add CS, that is similar and competitive with A, we have a similarity effect. That is, it will decrease the probability of selecting A. So we consider the asymmetrical dominance effect, the one we discussed before, the attraction effect. So here we are adding CA that is dominated by A, so it makes A look better, and so people will tend to choose it more than previously. And the third case is, for example, when we add an extreme option that makes A look like a compromise, and it will increase the probability of selecting A. So now let's see how the models we discussed before are able to model this. So we have the ground truth we showed previously. So we have these three examples, but the whole spectrum is considered. I mean, all the possible pixel positions. So the MNL is unable to represent this because of the independence of irrelevant alternatives. So there is no there is no effect in adding this third option. PCMC is able to do it, but we need to discretize to identify each one of these of the third alternatives. I mean, depending on its position on the feature space. So here we are discretizing with an 8 by 8 or no, yes, 8 by 8 grid. So, and okay, so the number of parameters is quadratic in this in the number of bins of the grid, and the PCMCNet is able to approximate it much better. And let's see here with, in fact, a much smaller number of parameters. Okay, so the picture corresponds to the last line of the table, and the rightmost column is the distance with respect to the true model. So the lower values are better. So we see that with about 600 parameters, we have a much better approximation than with more than 4,000 parameters in the case of PCMC. So this illustrates the amortized inference and the flexibility of this class. So on the real data set of airline itinerary choice, so the idea is that most of you are familiar with it. With this, is you have some query given by the user, some origin, destination, some dates, and you get a lot of options of itineraries with different prices, different airline combinations. So in this data set, we have about more than 30,000 booking sessions with up to 50 alternatives each. So this kind of data, it was shown in previous work that exhibits attraction effects. So it's relevant to think of the PCMC class to model this properly. We have parameters of the query that in fact we can see that as individual conditioning. So there's some specificities of the user, which specific travel trip they want to do. So this individual condition calls for PCMC-Net, since it is able to include this information. And it's important to notice that we have that more than 800 distinct distinct alternatives, and with 99% observed at most 7 times. So this is again the problem of if with PCMC we are not, it's not easy to model this because of the number of parameters required in the model, and also the problem of statistical scarcity that Jiri introduced in the beginning. So this calls again for PCMC-Net. Let's see the results in terms of prediction and top one accuracy. How good is the model to predict the actual choice? So PCMC-Net outperforms previous works, like ones using classical choice modeling approaches like MNL and latent class MNL, both of them using feature engineering, which is not necessary in PCMC-Net thanks to automatic feature learning. Then we also compare to recent machine learning approaches like random forest-based one and deep pointer networks-based one. So okay, so this is nice, but what about interpretability of the model? What is the model actually learning? Because classical choice theoretic models are good for interpretability. They have some choice economic axioms that are good for interpretation, and also linear forms that allow to easily interpret the coefficients. So what about these more complex models? So one way of interpreting choice models is using elasticity. So elasticity is a concept from economics. It's a measure of relative change of a variable Q, for example, quantity, in response to a relative change in another variable P, for example, price. So this is a classical demand curve. So the elasticity, so more precisely, the formula is the derivative of the quantity Q with respect to P, evaluated at some point A, multiplied by the price at that point and divided by the quantity at that point. So that makes it unitless. Okay, so some examples. So we have the same the demand shape. So this yields this elasticity. This is the absolute elasticity, so we're taking the negative. So it's a constant elasticity in this case of -1. So if we have a linear demand curve, in this case we have this other shape, and we classical economics identified three cases: elastic response, that is above 1, inelastic, that is below 1, and isoelastic, when it is exactly 1. So choice probabilities can be interpreted as normalized demand quantity or market shares. So, okay, so, and the idea that we're going to try to compute these elasticities for probabilities for different features, like price, for example. Derivatives are easy to compute for simple functions like those that are used for linear models. But what about the complex functions represented by neural networks like PCMC-Net? So here, this is a recent work with my colleagues from Amadeus, Rodrigo Acuña Agosta and Owen Thomas. This work is going to be published soon in the Journal of Revenue and Pricing Management. So here, to recap, the idea is that the elasticity formula requires computing the derivative of the choice probability with respect to a feature at a given point. And what is nice is that neural network libraries provide automatic differentiation, leveraging the fact that neural networks are a composition of simple functions by computing derivatives using basic formulas and the chain rule. So this is the basic mechanism that is used for training the neural networks. But now we are going to use it on a trained model. And now, instead of computing the derivatives with respect to the parameters, as it is used in the stochastic gradient descent, for example, we are going to use it with respect to the inputs we want to compute the elasticity with respect to. So, okay, for example, that is given a trained PCMC-Net model, the automatic differentiation mechanism allows to compute easily these derivatives on each data point. So, to end with this part, the price elasticity, for example, for the same data set I showed before. Now let's get some insights from the PCMC-Net model. So we can, for example, compute the price elasticity as a function of the stay duration. So for this, we're going to take the highest probability alternative of each set and compute the price elasticity. And we are going to aggregate the results by taking the median, because we are going to compute it on on some data set. Can be the same data set that was used for training or another one. In this case, it was computed on the same data set used for training. And we get, for example, this interesting result. We can split the data set into cases where the traveler is staying on a Saturday, which is a proxy for the trip purpose, because business travelers usually don't stay on Saturdays. So we see that for these travelers, the elasticity, they are quite inelastic for short stay durations. That they are insensitive to price changes. That is that in fact, when people need to travel for business, they need to travel, and they're not going to postpone or change the trip if the price changes. So they're still going to select the same alternative, the one that is more convenient. Okay, and the other category, in fact, is much more sensitive. Those that stay on Saturdays, and it increases as the stay duration increases. So we are plotting again the negative elasticity here. And so the takeaway messages: PCMC-Net equips the flexible PCMC class with feature-based amortized inference, individual conditioning. This allows stochastic gradient optimization with backpropagation, representation learning, application on data sets with large universes, like the one I showed for the airline itinerary choice. And also the last part is that it allows interpretability in terms of feature elasticity. In my example, it was price elasticity, and potentially other derivative-based measures that are easy to compute with automatic differentiation. So that's it. Thank you for your attention.
Yeah, thank you, Alix, a lot. This was very interesting work. I have few clarification questions before we engage in discussion. So can you elaborate a little bit more on contractibility and tell us what's the relationship with regularity?
Okay. Set. So
Mhm.
and so it's important to take into account this kind of structure to model actual behavior. So this is also the classical blue bus, red bus. So the cases where we add an alternative very similar to another one, and so in fact it will get a share of this option, but it won't get a share of the other. So it allows to structure the space in a reasonable way. So this is similar also to nested MNL models, if for those who are familiar with that. And so regularity is much more constraining in the sense that it's this property of, in fact, or axiom, depending on how you put it, of having if you increase the choice set, you can't have for a specific probability a higher probability of choice by increasing the choice set. So as I discussed, this uh, is a little bit constraining. I mean, it doesn't allow to represent context effects like the attraction effect, where the probability of choice increases by adding these third alternatives like the medium bucket of popcorn. Yes.
So that's then it implies that, if I understand correctly, that contractibility actually works with similarity effects.
Yes, they are related, of course, because
Mhm.
yes, we are like in a sense that they are similar. Yes, it's related to
Mhm.
similarity. Yes, yeah, of course.
And we have a question also about the representation layer. So would it be possible to go back in your slides to the
Yes.
architecture or the schema of the PCMCNet?
Yeah. Mm, yes.
So actually, how does the representation layer work? Because is it like embedding of alternatives?
Yes. Here the idea is to, for example, we have an alternative. In my example, I don't have to. I mean, the data is just numeric and categorical data. For
Mhm.
example, for categorical data, typically either you do a one-hot representation or some embedding of you learn some embedding for this type of data. Uh, but you could also consider more complex and unstructured data like images. For example, you could consider like the choice could be driven by some picture that you show to the user, for example. And in this case, you could use some convolutional network to get some useful features from the picture. So it could be anything that allows to get a useful representation of your features.
Mhm.
So it could be embedding layers or
Yeah,
whatever.
that's what I recall from your paper, and the fact that I really like that it can be, for example, applied for on text data, right?
Yes, yes.
Okay, Omar, do you have any questions regarding architecture or anything?
Yeah,
That,
I actually have a question about this specific slide. So if we walk through from the input until the end, right? So the presentation layer is basically you're trying to get latent representation or an embedding for the input. Am I
Yes,
right? And
yes,
then the Cartesian product is you're doing a dot product between them.
yes.
So that's gonna end
The
up
no, no, not the dot product, the Cartesian product. That
a
is, you
Cartesian
are,
product. Sorry.
yeah, you are obtaining every possible combination
Mm-hmm.
of the elements of S.
Uh, of element, yes, yes, and then you're feeding every single combination of those to a neural network,
Yes.
um, and then I'm a bit confused with the stationary distribution layer. What is that exactly?
Okay, this comes directly from the PCMC definition.
Mm-hmm.
So once you get the parameters of the Markov chain, the time continuous Markov chain, that is this matrix Q for the particular set S, you need to solve this linear equation, in fact, to obtain the stationary distribution. So in fact, it's a linear solver that will allow to give us the choice probability that in the end it is what we need to assess the likelihood on the data. So, and to train it with the stochastic gradient descent. So we're going to take this probability, this choice probability on the actual chosen, when we know which one was chosen from the training data, we need to compute the probability, the likelihood on this training data, and for this we need the choice probability.
So this obtains basically the score for each combination in the training data, right?
Yes, but the one that will be important is okay. Yes, no, not for each combination. Each combination we will have these transition rates that are contained in the matrix Q. But from this matrix Q, we just get a choice distribution for each element, individual element, each individual alternative. Okay, the final output is just a distribution over the set of alternatives.
Okay.
So the pairs are only necessary to build the matrix, but once we get the matrix, we solve this. I mean, the network, because it's included in the network, will solve the equation and just will output a probability distribution over the set of alternatives.
Awesome. Thank you.
Sure.
So, how much resources were needed to actually train such a model, like in terms of time and computation power?
Well, I trained it on a single machine with a GPU, and for a given set of hyperparameters, it takes, let's say, in some hours, like maybe depending on the parameters and how big is the network and so on, but about let's say 3 hours maybe, or 2, depending. And so yes, so this is can be on this specific data set of airline itineraries with about 30,000 choice sessions. And these choice sets are quite big, because some have up to 50 alternatives. So so this makes the data set a little bit big, because
Awesome.
And I also have 2 questions relating to the architecture or the feature. So first, regarding the individuals, what features did you consider? Did you have profiles of the individuals, or is it their behavior during the sessions?
Yeah. Okay. In fact, this is a good question. In fact, it allows me a little bit to clarify and to emphasize the difference between the classical recommender system, which I am not an expert on, but I know that usually information about the users is richer. Here, in fact, we have only the search request, that is only the origin, destination, and the dates, this kind of information. So maybe the search office, so the which is the channel where we got the search from, that is the travel agency or whatever, but we don't know much more than that. So we can just infer or compute more precisely some other characteristics, like for example, from the date we can compute, for example, if it includes a Saturday or not, or those kind of things. Also, if depending on the origin and destination, we can say if it is a continental trip or the domestic one, and this kind of stuff, but not more than that. We can't each search request. We only see the individuals once, and we don't know if they see them more than once. So we can't build a profile or whatever on the user. So this is an important point. But at least we know we can infer some stuff, but not too much. Yeah.
Okay, thank you for that. It clarifies my question a lot. Then I actually, because in paper you mentioned that the set of these individual features, it's stored in tuples, right?
Yes.
And it's allowed even to be an empty tuple.
Yes.
Why so?
Well, this is just to make the PCMC-Net generic enough. That meaning that if you have some applications where you don't have any information about the user, so you just want to build a choice model that is unconditional, but well, it's also possible to use PCMC-Net. I mean, the individual input is not required. It can be empty and everything will work fine. I mean, it's just to make it more generic. Yes.
I see. Thank you. And then I also recall that you elaborated actually on the previous work from Regan and Ugander.
Yes.
And there is actually a constraint, right, in PCMC that QI to QIJ are supposed to be positive. And in
Yes.
their work, they used sequential least square programming to maximize the log likelihood, right?
Yes.
However, it led to the violation of this constraint.
Yes, this is a problem that they observe. Yes, that's true. That they are able to fix it with some regularization at the cost of some efficacy of the model. Yes.
And do you recall what was their performance? Because they solved it with the regularization at the cost of the efficacy of the model. Do you recall what was that?
Well, no, not precisely. In fact, yes. In my experiments, I had to deal with this. I mean, on the synthetic data set, I run their code. Yeah, you also need to rerun many times for the optimization to have a good value. This is what I had to do. But yes, and I also had to add this regularization. I don't remember exactly what is the trade-off. I mean, how much you lose, but so I cannot tell you more on this.
Yeah, it's fine. I just recalled that and got curious.
Yeah.
But I also have a question on Omar, because right now we witness a lot of concerns about interpretability about a model, and this work is very related to recommender systems, specifically to your interest in session-based ones. And I would like to know how interpretability is important in recommender systems, and how possibly you can take Alix's work for designing a recommender system for bookings.
So as Alex mentioned, I think that the major difference between this work and a normal recommender system is the history. Does it present any signal that can be used in the next prediction or not? I like some websites online, they use session based to avoid this problem because usually the information is not in the history of the user, but the history of how the clicks happen. Interpretability for session-based is something that I never seen a paper on or any work on yet, and session-based recommendation. Maybe I'm wrong, but I because usually the way session-based recommendations work is you try to see what is the next click prediction based on all the previous sessions. So there's no any reason or there's no any specific features that contribute to the next prediction. It's just a sequence that you have. So I haven't seen anything in the interpretability part for the session based, but I will take that and I'll actually ask Alex another question, which is, as we mentioned, the major difference between the choice optimization and recommendation system is the history, right? My question will have basically two parts. Do you see the history of users if present? And I know this is not the case. But usually, if present, do you see this helping out in such a problem? In maybe trying to come up with a hybrid model of choice optimization and recommendation, and or do you see session based, like based on the sequence, could help out in deciding what's the next click?
Yeah, I think yeah, that's an interesting point, and I think it could such information I think could be useful to enrich and make the model more powerful. I mean, it's we are able to just give it to the model through the input, the individual input, and with some good representation. Let's say if you're, for example, you have a list of I don't know, previous steps taken by the user, or of clicks or whatever.
Bookings.
So it
Yeah.
also could be represented, for example, with a list, a sequence
Mhm.
that could be input in the neural network with some appropriate architecture, like maybe an RNN or some convolutional network for sequences. So I guess it could be perfectly
Beneficial.
adapted to those such scenarios, and it could take advantage of richer information. I mean, yeah,
I tend to agree with you. Like I feel the click sequences will add information, but the history of booking for a user might not, because you never know what's the next trip you're gonna have, right? Unless you're very
yeah.
consistent on making a specific trip every year. Other
Hmm.
than that, I don't think the history of booking will matter. Maybe the prices of it will matter, but what makes more sense and what I think there might be more signal and more richer information is through the click sequences, right? Like what was the trip that you took to end up in this specific itinerary? I think that, yeah, that might help.
Okay, yeah.
And yeah,
Mm. Yeah, it
that's
makes sense. Mm.
mhm. um, I I have kind of another question. So, in here, when you're doing the Cartesian product, right? You're trying to come up with every single combination between the user, and is it all the combinations present, or just the alternative for that specific thing? Because I'm a bit confused in that part.
Sorry, I didn't get your question. Can you
Okay,
repeat it, please?
so in the Cartesian product layer,
Yes.
basically you're trying to get the combination between every single item, or just the item with its alternative.
Every single item in the considered set, no?
Yeah.
This,
Okay.
okay.
So
Not in
it's
the
technically,
universe,
yes.
because
Okay. Yeah.
we
That.
would be getting back to the problem we have with the original PCMC, that we need the transition rate for every pair of alternatives in the universe. Here it is for the current session under consideration, or let's say we are batch mini batch training, and so we are going to consider a number of choice sets. So for each one of these choice sets, we're going to build all the pairwise combinations.
Okay. That makes more sense. Now I understand.
Okay, thank you.
Okay, and one more question about the architecture. So I see if I understand correctly, the input layer and representation layer. Again, if I wanted to add more features, it would
Yes.
be concatenated in the similar manner, right? It doesn't change the approach.
No. It's, I mean, each SI, each alternative SI is a tuple of features. So it can have one number, one text, an image, whatever you want. So it's a tuple containing all the features, and yeah, you can add whatever you want, and that doesn't change the approach. It's just that it will change the specific components you will use in your representation layer to finally encode each alternative as a numeric vector. This is what we need before before the Cartesian product layer. We need a numeric vector for each alternative, and then we just concatenate them with this Cartesian product.
Okay, thanks, Omar. We went through a lot of a lot of assumptions, a lot of theoretical framework like context effects and etc. and interpretability. You already expressed that you haven't seen this kind of work in sessions-based systems, but in general, in recommender systems, do you see a space for incorporating these knowledge from behavioral economics?
For sure, like there's a lot of cases where the history is not either present or it's not enough, right? So, um, I worked on a project before where the history is for each user there's one or two choices, right? So
Mhm.
you're talking about 99.7% sparsity if you decide to take it into in the traditional recommender systems approach. So at this point, I don't see recommendation system work the way they should work. So in this case, it's going to be as explained here, like choice optimization is going to be the key to be able to have a prediction of what might fit the user. And the user in this case is a query representation. Maybe the history can be additional information for the presentation of that user, but I don't think at all the history by itself will be enough. So I know a lot of cases where there's no enough history. In this case, like choice optimization can be the key. And even if there's history, you can always try to have that merging hybrid model between those two weighted mix or whatever.
Yeah.
But I think that could help a lot.
Yeah, thanks. Because
Interesting.
Omar and I, we just had we had a chat a week ago, and I actually said, look, I started viewing recommender systems as basically as choice modeling, and I thought I think there is a lot of space for in recommender systems in incorporating these theoretical frameworks from behavioral economics.
Hmm.
Because as we just saw, and actually your work, Alex, is not has been previous attempts in choice modeling that injecting knowledge from psychology and from what we know about how humans make decisions. It actually improves accuracy and also the speed how a model can learn. So, any other questions, or can we move to the discussion? I mean, next questions.
Yeah.
So, for the authors, if anyone has any question, please type it in the live chat. We can take it to the author. Until the comes the question, you can go to the next point.
Okay, and I actually like this question. So imagine, or Alex, imagine a set of different classes of models satisfying less and less assumptions. So,
Yeah.
for example, Luke's axiom, regularity, and transitivity, and there would be three models. So, for example, model one would satisfy all of these assumptions. Model two satisfies only regularity and transitivity, and model 3 satisfies only transitivity. So when running the same experiment with this, on these models individually, what would one experience in terms of performance and bias and other interesting observations?
Yes, thank you for your question. Well, of course, less structural properties means more degrees of freedom and potentially the ability to learn more complex behaviors and to have also a better predictive performance on such complex data sets. Nevertheless, it comes at the cost of more parameters to learn and also possibly a more difficult inference. That is the case, for example, for the nested MNL model that I mentioned before. On the other hand, structural properties are not only restrictions, but also a way of imposing some behavior that is considered natural, as you mentioned before, that from psychology, from behavioral economics. So it's a guarantee that the model will not learn crazy stuff just to fit data. So it's from a machine learning perspective, it's regularization since you are constraining your model class. But from a choice theoretic perspective, these constraints can have some behavioral economic meaning or some psychological meaning that we want to inject in the model. It's like, for example, in image processing, when you are using deep neural networks, you want translation and rotational invariance. So you want to have this kind of behavior, so that you inject this behavior in your architecture. So this is similar. You want some reasonable properties to be satisfied by your model. So you, in that sense, you constrained. It's not only a bad thing, but it can be a good thing to have such properties, like, for example, the ones I discussed previously. Yes.
Okay, thank you.
Thank you.
Awesome.
And I also, okay, so I already asked about this constraint of Qij plus Qji to be positive
Yes.
In the architecture slide. So, and you specifically consider this constraint to be greater than 0 to guarantee that the chain has a single close communicating class to imply the existence of unicity of stationary
Yeah.
distribution. So first, what does unicity mean in the context of PCMC?
Yes. No, I mean, what we are looking for is that to have a unique choice distribution. This is what we want to have, a well-defined choice model. We need to the existence and the unicity of the choice distribution. In the case of PCMC, this choice distribution comes from the Markov chain, and it is more precisely the stationary distribution of the Markov chain. So in order to guarantee its existence, a sufficient condition is to have these transition rates. I mean, the sum of Qij plus Qja to Ja to I to be positive, and so this is a sufficient condition to ensure that the existence and the unicity of the stationary distribution. In fact,
I see.
yes, sorry.
Yeah, because then I also noticed that in the previous work of Regain and Ugander, they
Yes.
constrain Qij and Qji to be greater or equal 1, as
Yes.
opposed to your approach to ensure irreducibility, which
Yes.
is one of the Markov chain property.
Mhm.
So can you explain the two different approaches?
Yeah, no, in fact, they are the same. It's just the what is necessary is to have this sum to be positive, and in fact, we can also say to be greater or equal than 1 as Regain and Ugander, or some epsilon as I do in my network that you can choose arbitrarily. So because in fact, if you multiply all the matrix of transition rates by some constant positive number, you will get the same stationary distribution. So in fact, it's equivalent to either impose a greater or equal than 1, or greater or equal than epsilon, or simply to say that it's positive, because we can do this manipulation and we will get an equivalent model. Yeah.
I see. Okay. Awesome. Thank you. So Omar, would you have anything? Would you like to ask Alix anything as well?
No, thanks a lot, Alex, for your talk. It's really nice to have a different point of view for this. It's really good work. Well done, and really well done on publishing a paper by yourself.
Thank you very much, and thank you for the interesting discussion with the connection with a recommender system that I really interested in exploring. And yeah, thank you both for your questions and hosting this session and inviting me.
Yeah, thank you, Alix, again, because you made this actually happen. This was actually very interesting work, and I liked reading it. And thank you also everyone who watched our session. Please make sure you subscribe to our YouTube channel ML Papers Explains to get notified about all the live sessions and other free content we publish. We currently have about 15 different streams that are focused on various ML topics, and this session in ML in economics stream is one of them. So hope you enjoyed and you will come back. Thank you a lot. Goodbye.
Thank you. Bye.